Thanks for click. In this video, I would like to introduce a general process for creating 3D models of a human-shaped robot, and the animations of its walking. This kind of project, I think, can be done on any parametric 3D modeling software similarly. I used FreeCAD version 0.20. This robot is trying to imitate the Moonwalk. This robot was badly modeled at first. It walks a little abnormally. Beginning this project, the first step I had to do, was to examine the movement pattern of the human leg and foot during walking. I adopted this type of sketch for describing the movement pattern and drew my own sketch to imitate a human leg. It is divided into 21 moments formations for one stride walking. Here, the beginning formation becomes the same as the last formation to be repeated. The lower part of this model is composed of 4 segments. They are toe, foot, lower leg, and upper leg. At least one of the 2 toes is touching the ground during walking, and the toe angle to the ground is changing during walking. The angle between the toe and the foot body at the metatarsal joint is changing to some extent. The angle between the foot and the lower leg at the ankle joint is also changing to some extent, and also, the angle between the lower leg and the upper leg at the knee joint is changing. The 2 walking legs are linked to the hip. Because I assumed this human robot to move horizontally in the x-axis direction in the 3D space, I designed the x-coordinate value of the upper end of the right leg to be the same as that of the left leg. And I set up this value on the x-coordinate as the reference value. Changing this reference value means the 2 upper ends of this robot's legs move horizontally accordingly. Now, for the animation of the walking action of the leg, I set up a certain equation with which the knee angle could be calculated depending on the reference value. Changing this reference value means the knee angle changes. I applied this equation to the knee angle value in the sketch constraint of the leg, and I could have the knee to be bent or straightened simultaneously, according to the horizontal movement of the leg. In this way, by setting up all the other necessary equations for the other values, such as the foot angle value from the ground, and applying them to the sketch constraints, I could have the whole leg formation change simultaneously according to the reference value changes. The sketch for the modeling of the leg has to be fully constrained, in order not to be collapsed while its formation is changing. After some trial and error, I selected 5 constraints for each leg in the sketch, to be expressed by the equation and changed according to the reference value change. These are the x and y position of the toe angle from the ground, the angle between the toe and the foot, which I called the meta angle, and the knee angle. The lengths of all the segments were fixed. On the initial sketch, showing the walking pattern with the 21 formations, I checked all the values of those constraints one by one. These initial raw data were arranged in a spreadsheet like LibreOffice Calc. The data in the first row is the reference value, which is the horizontal position on the x-axis of the upper end of the leg. With this data table and the graphing tool in the spreadsheet, I got several graphs showing the changing trend of each constraint. With the parametric 3D modeling software, in this case, FreeCAD, I made one base sketch, to represent the formation of the 2 legs, at a certain moment during walking. This base sketch was commonly used for the modeling of each leg, with the help of the shape binder tool in FreeCAD. In this base sketch, temporary values of those constraints were applied. Equations for the movement of the leg were not yet created. Those were going to be applied later. From the data and graphs gotten in the previous step, those equations for the formation changing during walking were created, expressed by the reference value, sometimes with the help of the trend line equation tool in the spreadsheet software, and sometimes by reference to the graph drawing sites. These equations could be polynomial or modulo functions, according to the characteristic of the movement. In any case, because the walk pattern is repeated during walking, the created graphs have repeating lines with each stride period. I replaced those dimensions and angle values written in numbers in the initial base sketch, with these equations. The original equations looked very long and complicated. I utilized the spreadsheet embedded in FreeCAD, to be clear in the input line. I made 3D models of the upper body, the arms, and the head separately. The upper body was assembled to the hip, which was connected to the leg, and driven by the movement of the hip. The head and arms were assembled to this body, and driven by the movement of the body. Finally, trial animation was done on the assembly for workbench in FreeCAD, with the reference value as the primary variable, and reviewed. Reviewing the initial animation, the tuning of the robot action could be done thanks to using this parametric 3D modeling software. I modified initial data and graphs and accordingly modified those equations for each constraint. Additionally, for the two arms to swing forward and backward, relative to the body, trigonometric equations, dependent on the primary variable, were applied to the assembled angle of the arms to the main body. For the moonwalk action of this robot, the movement pattern of the leg was completely modified with a fixed height of the toe, a fixed meta angle, and a fixed height of the hip. Thanks for watching.